I'm still being pulled pretty strongly towards the Earth. Let's assume I don't disintegrate, and the camera doesn't disintegrate. We are the two constants in the universe. If we could go where the planet disintegrates, then we potentially would be drawn towards each other.
Okay. But is like the pull of the Earth so strong that it like just negates any movement towards the camera?
Yeah, pretty much, because there's friction between me and the carpet. But if I had the camera and the camera was sitting there and I'm here and we're in the middle of no gravitational field from anything other than just the two of us,
Yeah.
we would be attracted to each other. How much time it would take? Well, considering that force, the camera would move more than I would because it has a smaller mass, so its acceleration would be greater. But still, it's a pretty small acceleration. It would take a while.
There was a simulation I saw with two baseballs out in space that were 7 meters apart, and I think it took like 2 weeks for them to come together.
Okay. So we're farther apart, and I guess my mass is more than the baseball, so that's less than one. I think it's a 251 problem where I've got, because recognize as we get closer, the gravitational pull increases also, so it becomes a calculus problem.
So you telling me I could just pick my phone up one day? My phone would just fool me one day. Like,
Now the gravitational pull between the phone and your hand is tiny compared to the gravitational pull between the phone and the ground. So
Earth is just messing up everybody's powers.
now, when I was in high school, and I think this is bunk, but when I was in high school, my physics instructor basically said, if you feel like there's someone behind you, but you don't hear them, but you feel like someone's behind you, he said that was that you're sensing that small little gravitational pull. I posed this to one of the professors at USC who diplomatically said, I've never heard that before.
The sixth
Doesn't seem
sense?
like
You talking
one.
about the sixth sense? Like when you feel a presence?
Possibly. The pull is so small, I really don't think you do it. I think what you actually are hearing is probably muted sound or the body heat or something like that.
What's muted?
But anyway, I present this information from someone who eventually goes to jail for contributing to the delinquency of a minor.
What is muted sound?
I don't know
So
why.
my sixth sense is all things physics.
It's still going, right?
So you telling me, okay, I got another one. So you telling me, say like if I close my eyes and I focus real hard, would I be able to feel everybody's presence? Or is that just,
It would be so small, I doubt it. However, have you read or listened to Hitchhiker's Guide to the Galaxy? That was a no. They do play upon that a little bit, that if you could, they call it, it's a fairy cake, and I'm not, it's some British thing, but you have a fairy cake, and it's experiencing forces from everything in the universe, and then from that you would know where everything is. It's comical science fiction. Douglas Adams liked to take those little ideas and just blow it out of proportion.
I'm trying to get powers?
All right, so we have this force. This is the generalized force. If I knew what the little g was between the acceleration of gravity that I would cause that camera, then I could have used mg. But for typically we don't calculate those. But what the heck? Let's go ahead and calculate it. What is the acceleration of gravity because of acceleration due to my gravitational pull for an object 3.5 meters away? Well, in essence, I'm taking my formula right there, my big G,
Those numbers are trash.
mass 1, mass 2, over r squared, and I'm starting to set that equal to the gravitational pull. So this is mass of George times mass of object. That's mass of object times G. I can figure out the gravitational acceleration because of myself. And so acceleration due to gravity would be G times the mass of the central object over the distance squared. So 6.67 times 10 to the negative 11th times my mass divided by the distance squared. Which should be 5.4 times 10 to the negative 10th meters per second squared.
So what we just found is your gravitational pull on an object 3.5 meters away.
The acceleration due to gravity, 3.5 meters. The acceleration due to my gravitational field, 3.5 meters away.
So how would the formula be any different for an object that was 3.5 meters away from you? But that hadn't necessarily had like a different mass. Would it be the exact same?
I mean, a different object, 3.5 meters away?
The same object, but how would there be a different way to calculate that object's pull on you?
The difference would be instead of 100 here, you'd have 0.01. So it all comes down to this constant over the distance squared times the mass of whatever is the central object. Go
Is
ahead.
that acceleration due to your gravity proportional to your surface area?
No, I am assuming I'm a point mass.
Okay, so it's only like giant spheres.
Yeah. If we got into things that were not spherical in shape or could not be approximated as such, then it could be a potentially really messy calculus problem. I am assuming that it is 3.5 meters away from all of me.
But say a chair 3.5 meters away from you would experience the exact same force?
You said a chair?
Yeah.
The acceleration to gravity would be the same from me, but the force would be different because the mass would be different.
Yeah, okay.
I assume that the chair is more than 10 grams. But this is one of the reasons, and also when we're dealing with weight, of why in physics we can't call mass weight. I know in biology they tend to use mass and weight interchangeably, but in physics, no.
Okay, so what law of Newton's would Star Wars be ignoring exactly with the Force?
So to be able to move something from where there's not direct contact, historically it was called action at a distance. And gravitational force seems to have an action at a distance, the fact that I don't have to touch the earth to be pulled by it. The electric and magnetic forces also, and electromagnetic forces also can do action at a distance. So in order for the metachlorine mythology to work, I need to somehow be able to exert a force on whatever the object is without touching it. So, but by Newton's third law, if let's say I took that desk, the table right there, and I moved it across the room, it would exert a force on me also by Newton's third law. So it seems like Newton's third law is violated.
Makes sense. So there goes my force.
And faster than light travel, like the Millennium Falcon when it jumps to hyperspace, that does not violate any of Newton's laws.
So you tell me I can jump to hyperspace?
No. I said it didn't violate Newton's laws. We gotten an update since then.
What is the theory about if you travel faster than the speed of time, or speed of light, you go back in time?
Same force that I'm using.
It's one of Einstein's.
So what if I try to flip a car?
We need to redefine time at that point. I talked about tachyons in here, didn't I?
tachyons, now we talking about the Flash, Lord have mercy.
Oh, yeah. A tachyon, so if you look at special relativity, which I would cover near the end of 152, there's this expression that pops up of 1 over the square root of 1 minus v squared over c squared. All right. This shows up enough, they give it a special letter, the gamma, known as the Lorentz factor. V is how fast the object's moving, and c is the speed of light. Now, if an object is going the speed of light, we get 1 minus 1 in the denominator, or 0, and obviously, mathematicians still haven't figured out how to do that yet. How do you divide by 0? From that, it has been theorized, and there's a lot of evidence to support it. It's theorized that anything that starts out slower than the speed of light can never go faster. Anything that starts out faster than the speed of light will never go slower. That is a barrier that you cannot cross.
The Flash does that like it's
Yeah. The Flash also would kill a number of people too. That
like hero he is.
you've got the person in the road and the car's coming towards him, and the Flash comes and grabs the person and jerks the person out of the way of the harm of the truck. Well, to zip in and whip the person away, the person would experience so much acceleration that basically, as in a car accident, that if I move my frame very quickly, my heart does not move as quickly, and that would, it would kill me. I have better luck getting hit by the truck than having the Flash pull me out of the way in the nick of time. And there was a Spider-Man comic book where someone was falling, and Spider-Man hit him with the web, hit whoever was with the web, and later revealed that Spider-Man actually killed the person because he stopped the person so quickly. There's I think it's the University of Michigan professor who does a physics of comic books, or sorry, superheroes.
Alright, so I got another question about the Flash. So, there's one episode, he vibrated his hand so fast and it shredded somebody's heart. How would that even be a thing at this point?
It would shred the person's heart.
Like, he vibrated, I can't explain. He
It vibrated the hand through
his chest. Like, would you be able to would you ever be able to go fast enough to phase through somebody? Like, is that possible?
Theoretically, I'm assuming that what they're going for there is that everything we're made of, everything around us is vibrating at a certain frequency. And the general idea in science fiction is that if you can match that frequency, you can sort of pass through each other. There is something called the Bose-Einstein condensate that actually has been found at this point, where if I shine two beams of light, they will pass through each other. If I throw two baseballs together, they will not pass through each other. That is because light is what's called an integral spin particle, and baseballs are filled with electrons and protons and neutrons, which are all half spins. Half spin particles cannot pass through each other. If you've done chemistry, have you had chemistry?
Not yet.
Okay. In chemistry, they talk about you can't have two electrons with the same quantum numbers around an atom. It's all related to that. So, but if I have two half-spin particles, it is possible for me to combine two half-spin particles to create a whole spin particle. And so if I do that, if I take a simple atom, like take a hydrogen, strip away the electrons, so I just got a proton there. I get them just right, so they're two half-spin particles, I can make a whole spin particle without them. So I now then I guess I need a helium nucleus, because I got two protons already there. I take another helium nucleus, and it has two protons, and I get them to align just right, so they're a whole spin particle. I now theoretically can take those two whole spin particles and pass them through each other. So yes, it is theoretically possible for one object to pass through another if all the spins align just right. Now, at this point, we can do it to a couple of atoms. We're not to, we're not to anything that we could actually see with the naked eye.
Alright, I'm good.
Okay. Let's connect this with the others, with what we were doing on Thursday. Earth. Moon. Force diagram. I got this gravitational pull, F sub G, F sub G. It's traveling in a circle. I'm assuming no air resistance in outer space. In other words, this is the only force acting on it, and it's pointing towards the center of this path here, which makes it a centripetal force. If I plug into Newton's laws, I know F equals ma. I'm going to make that direction positive. Then I have F sub G is equal to the mass of the moon times the centripetal acceleration. That's my equation of motion right there. We plug in the formulas. We have an independent formula now for the force due to gravity. That's big G, mass of Earth, mass of moon, over that distance, the Earth-Moon distance, squared, is equal to the mass of the moon times the speed of the moon squared over r. Well, mass of the moon cancels out. And I'm just going to bring the r's over. So I got G times the mass of the Earth is equal to v squared r. This is the distance between the Earth and the moon, and that's the radius of the path, which we are assuming is the same. Now speed. What is the formula for speed? Average speed.
Distance over time.
All right, so we have distance over time. If this moon is traveling in a circular path, what would be the distance?
Can you repeat that?
Circumference.
Yeah. If the moon is traveling in a circular path around the Earth, what would be that distance?
Oh,
And the formula for circumference?
2 pi r.
And the change in time, if I can do that one a little bit better, barely. I'm using the capital T to indicate period. It's the time it takes for an object to go around, for repetitive motion to happen once. So this is known as the period. One of the reasons why I don't use T for tension. Period, and this is the time to complete one cycle of repetitive motion. So I'm just going to plug that in. Since that's my speed, I can plug it into here. So I've got G times the mass of the Earth is equal to 2 pi r over big T squared times r. I just square everything inside there. I'm going to get a 4 pi squared. Now, you know what? I'll go through the extra step. Mass of the Earth is equal to 4 pi squared r squared over T squared times r. I'm going to get T and r on one side and everything else on the other. So I get G times the mass of the Earth over 4, and that's just a straight mark right there. What are the chances I can hit that? Boom. G times the mass of the earth over 4 pi squared is equal to r cubed over t squared. We can now predict how far away the moon is from the earth. Or if we know that distance, we can predict the mass of the earth, but since I know the mass of the earth off the top of my head, we'll go that route. So I'm saying that big G, so that's 6.67 times 10 to the, that's not much better. I think I keep putting the good markers over there. 10 to the negative 11 Newton meters squared per kilogram squared, times the mass of the earth, 6.38. That's the radius. 5.98 times 10 to the 24th kilograms, divided by 4 pi squared, equals the radius of that path over the period squared. So, what is the period of the moon going around the earth?
What is the what?
Period. How long does it take for the moon to go all the way around the earth?
24 hours.
That's only from our point of view.
Oh, it's,
Not in space,
Yeah, about a month, 28 days or somewhere around 28 days.
but the moon to go around the earth.
Yeah,
that's how long it takes to go from like a full moon to.
Yeah, the moon's
full moon to full moon. Ish.
Huh?
We're spinning as it's doing. I mean, the moon's traveling like this and we're spinning faster than that. So it looks to us like it hasn't moved very far.
I
But,
was about to say, what is going on?
all right. So we can now predict it. Now we do have one issue here, the fact that newtons, meters, kilograms are all nice SI units, but days is not. So if I want meters in my final answer, and I do, we need to get this into seconds. So how many seconds in a day?
Maybe like 5,000 something.
What'd you say?
Don't worry about it. Google will tell you everything I need to know.
All right.
86,000.